necessary yet. Like, sure, okay. Fine. Yeah.
Rohan, if you are writing something, please. Are you
No, I'm
writing
not
something?
writing on, not nothing on the screen. No.
Oh, okay, okay.
I'm just making my own notes for the lecture. I'm just like, yeah, just going through everything so that I don't miss something. That's all. Proof also, just proof. Proof is always necessary. All right. Hi everyone. How are you? Hello.
Hello, we can hear you, Rohan.
Yeah, yeah. I'm just saying hi. How are you?
Oh, okay.
All right. Good. So the target today is just to show you some cool ideas and proofs. There's like not much content. That like I'm going to not introduce any theory or anything. I'm just going to uh, present some nice proofs I think are nice of some results you hopefully know. Like first is one is FLT, which is Fermat's little theorem. Which states that a to the p minus 1, okay, for convenience I'll just say p divides a to the p minus a. Yeah. Second is Wilson's theorem, which says p divides p minus 1 factorial plus 1. And third is AMGM, which states x1 plus x2 plus xn greater than or equal to n and the root of x1 xn, where x1 x2 xn are non-negative reals. Yeah. So these are three results you hopefully know. Yeah. Have any of you not seen any of these before? Or like if you've not seen some subset of these before?
It's divided by n, am.
No, I mean I took the n on the other side.
Okay, okay. I didn't see.
Have you seen, like, any of you who have not seen these results?
No, I've seen many times.
Okay. So what we'll do today is I'll plan to present 6 proofs of Fermat's little theorem. For Wilson's, I'll present 3-4 proofs depending on time. For AMGM, I'll probably present 5 proofs. You can make up more. I know at least 8, so you can make more proofs. But I think I'll go over 5 ideas at least. Yeah, so this is the plan for today. Any of you have not seen these statements before? You can speak up. I think that's preferable if you all speak something.
I have seen all three.
Okay. Cool. So I'll start with FLT. So FLT, you want to prove that a to the p minus a is divisible by p. So one natural thing that you would usually want to try is just try to induct, right? So the first proof is just induct. And how do you try to induct? You try to go from a to a plus 1. So what is a plus 1 to the p? It's a to the p plus p choose 1.
Binomial theorem.
Yes, exactly. So it p choose 2 to the p minus 2, just dot all the way up till p choose p minus 1 into a plus 1, right? This is the form by binomial theorem. Now observe that all of these terms are divisible by p, just because they're of the form p factorial upon I factorial into n minus I factorial. And this is not divisible by p, this is not divisible by p, but this is divisible by p. So the resulting term must also be divisible by p. So all of these you can remove. So you're just left with a to the p plus 1. But by your inductive claim, a to the p is a plus 1. What? Very clean induction, and you don't really have to do anything much. Second is, I don't really need, just because of this idea that I did right here, I don't really need it to be a. I can make it 1 plus 1 plus 1 plus 1 to the p. These are a of these. So this is, again, just by the previous idea, you'll have p factorial upon some sequence of factorials, right? So it will be what? P factorial upon r1, r2, r1 factorial, r2 factorial, ra factorial, where summation ri is equal to p. Yeah, this is the form you'll have. But this is again 1 plus 1 plus 1 plus 1 is equal to n. It will just be a1s, right? When one of them is p and the others are 0. So whichever one is p, you can pick. There are a choices. So it's a. Yeah. So this is your second standard proof. Now I like these proofs I think you might have seen before. But from the third proof, some of you might have seen, but I hope like it is interesting or new for some of you. And I feel like this proof in particular is very instructive. So consider the set of things which are 1, 2, all the way up to p minus 1. Okay. And I change this to the set of things which are a, 2a.
P minus 1.
Yes, precisely.
P minus 1 A. Mod P.
Yes. Right now I just changed it to this set.
Product of set.
Now when I look mod p, observe that all of these must be different. Just because if IA is congruent to JA mod p, that means that
I is
p
congruent.
divides A into I minus J, which implies p divides I minus J, but I minus J is smaller than p. So that's not possible. So all of these are distinct mod p. Like the remainder they leave when I divide by p is different. A2, A3A, all the way up to p minus 1A. So when I check the remainder, it must be basically 1 to p minus 1 in some different order possibly. So the product of all these when I'm looking mod p is just the product of all these when I'm looking mod p. So this is p minus 1 factorial is congruent to a to the p minus 1 factorial. And since p minus 1 factorial is common, I can remove it. And obviously p does not divide p minus 1 factorial, which is crucial. So you have a to the p minus 1 is congruent to 1 mod p. Okay. So I went over 3 decent proofs quickly. So if you didn't get any of these, do tell me.
In the third proof, you said that like if any of them raise the same remainder when divided by p, then p must divide I minus j, but p can divide a also. So
So
that
sorry,
is also possible.
yeah, we are assuming that p does not divide a. I should have mentioned. We're assuming here that p does not divide a, because if p divides a, then clearly p divides a to the p minus a. So I just took that case, assumed it. I should have mentioned, sorry.
Okay.
Yeah. So if you get this, and then you can just multiply with a, and you'll get the desired result. Okay. Any doubts so far? You can ask and I can repeat.
How did you solve that proof 2?
How did I do the second proof?
Yeah.
Okay. So what is this? Just like by multinomial expansion instead of binomial, what is this equal to? It's what? Summation O1, R1, R2, RA says that the sum of all these RA is equal to P, and you're doing P R1, R2, RA into 1 to the P, right? Now this is divisible by P if any two of them are non-zero. So you only consider cases where exactly one is non-zero and the others are 0. So there are A cases for that. So it's A into 1 to the P. So it's just A. This is slightly tricky because you need to know what the multinomial theorem is saying in some sense, but don't worry too much about it. I just mentioned it because I wanted to just show that the fact that because you can carry this out for inductively, this is a natural thing you're trying. You don't need to actually do it just inductively. You could have done it directly as well. Yeah, but don't worry about it. Okay, for the others, any doubts?
Could you explain the third one once?
Okay, so what I said is like just consider the set 1 to p minus 1. These are all of the different remainders when you look mod p, right? Except 0.
Yeah.
So when I multiply it by a, I get another, again I get p minus 1 remainders, yes?
Yeah.
Observe that none of these are 0 again, just because p does not divide any of them. So, and none of these two are same as well when I check the remainder. Because if they were same, then I could just take the difference, which should be divisible by p. But the difference of any two of these is not divisible by p.
Okay, I got it.
Yes, so the product must be the same. So we get the desired result. Awesome. Okay. So here's where it gets interesting. This is a very cool proof now. These are good ideas. I particularly like the third one. Feel like it has. You should be able to come up with such arguments eventually. It's a good class of ideas. But 4 is where things start getting interesting.
Hey,
So
what
what you
if p is a prime number?
we're only working when p is a prime.
It's not a raised to the p congruent a mod p when p is prime for all a.
That's what we said.
Uh, if p is a prime, then we can write this from our little theorem as a raised to the power p congruent to a mod p for all
That's what we
a.
are trying. That's what we are trying to show. That was the goal. We are trying to prove that theorem that you just claimed. That's
Okay.
Comet's little theorem, and we are just giving different proofs of the theorem.
Okay.
Like it's not something you can just assume, right? Like it's not something that just magically comes out of there and is axiomatic. It's something that you have to prove. So we're just giving proofs of it. Okay. Okay, so consider the following structure. Let's say you have a necklace with p beads. Okay. You have this necklace with p beads. Okay. This is your necklace. It's a complete circle, by the way. Now you have a choices of bead colors at every stage. Like you have a different colors of beads, and you can try to make a necklace in any way. Okay. But the thing about necklaces is, like, even if you rotate them, it shouldn't matter. It's the same necklace, right? It's the same necklace if you rotate. So how many different necklaces can I make?
P minus 1 factorial.
Why? I can how? Sorry.
Factorial necklaces.
What? Could you repeat?
P minus 1 factorial necklaces, right?
Why? I have
Um,
I have to put in p beads,
yeah.
and I have a colors. I can make any bead of any color.
Then should be like a to the power p minus 1, a to the power
Why?
p. Well, each bead has a choice of a, how say this, a colors, right? Each bead.
Okay. But and why minus one?
Uh, sorry, I didn't mean minus 1. Each then a to the power p choices for all of the beads, right?
You say okay, sure. But now you're considering rotations again, right? You
Yeah.
shouldn't be considering rotations.
Okay. Um, should I be considering the rotations?
Like you're in the sense you're considering every like in the same necklace you're considering multiple times, but just even considering its rotation.
Yeah. So shouldn't be like a to the power p over p.
Is
Like
that necessarily the case?
um, not necessarily. Each of them can all be of the same color, so the rotation matter.
Yes, exactly. So you have to consider the cases where the rotation does not change much.
Yeah.
Like even if you rotate, you are getting the same thing.
Yeah. Right. So in the case where the total number of total number of necklace combinations are a to the power p minus the number of times there's like no change in the color. All colors are the same. That one is a cases. So if you divide it by the total possible rotation which is p, you can rotate all the bits to p. This has to be an integer number, right?
Plus a. You shouldn't forget that. Right now we are just counting the number of necklaces.
Right. Plus a. So this should be an integer, right?
Yes.
So if it's an integer, that means a to the power p minus a over p has to be an integer.
Yeah.
So that will just give us the proof.
Yeah, that's it. So what just happened is, sorry, excuse me. We have p beads, and we have like a colors of beads, and now we want to put in beads. So for every bead, we have a options, right? So we have total a to the p beads. But since we're also not like, we don't care if it's the same necklace via rotation. So we just check, okay, if I rotate it by anything, I'm always getting a new necklace, right? If I'm always getting a new necklace, then I'm happy. Then I could divide into groups of p. If I'm getting the same necklace on rotating a bit, then I should be wary of this case. So how many necklaces are there in which you rotate and nothing changes?
A.
Exactly a. Just because in that everything has to have the same color. So the number of resulting necklaces is a to the p minus a upon p plus a. The a that we had left out initially. Like you can ignore these, consider the remaining necklaces, divide by p and add those back. Yeah. So this means that this is an integer, which concludes.
Why are we subtracting e?
Oh, so like I was trying to count like how many necklaces are there, right? So I'm considering the cases. There are two cases. One in which like nothing, like the rotational. If I rotate, I get a new necklace, and the case where nothing rotating changes anything. Right? So rotating does not change anything in A cases, and a to the p minus Manoj, you're unmuted. Could you please
Sorry.
mute yourself? No
Okay,
problem.
now I need.
Okay, you got it?
I apologize.
No problem, no problem. Okay. Awesome. So this is a very cool proof, and this is called the necklace proof. Yeah, it's a very nice argument to know.
Please, can you repeat the fourth proof, please? Fourth one.
So just ask, Ravi. You can ask. So there are p beads in a necklace, okay? And
Okay.
each bead you can color, and you have like what color watercolors nearby, and you have eight different colors, so you can paint each bead. So how many ways can you color it, the necklace?
A to the power p.
A to the power p, precisely. But now, like, just because it's a necklace, like rotating shouldn't change anything. Like you're going to wear it the same way, like it will look exactly the same.
Rotating as in, do we swap the places of beats?
What do you mean?
Do we swap the places of the beats?
No. I mean, okay, if I gave you a necklace, instead of wearing it directly, you could just rotate it a bit and wear it, right? So for you, it's the same thing. So I'm just trying to find out how many different necklaces I could have given you that would seem different to you.
So I think what he is trying to say is that when you would swap the beads, would that make a new necklace?
That could make a new necklace. If they're of the different color, then it's a new necklace for me, right? But if it is the same color, then for me, nothing changes. Right, so there are a to the p things. Now we want to put all the things which are rotations of one another in the same group, right, of things. So there are a things which don't change in the rotation at all. So they're in their own individual groups of size 1. These are a things. And the rest are in groups of p. So these are a to the p minus a things in groups of p. So there must be a to the p minus a upon p groups. And this is the part where we care it's a prime, just because you're saying that on rotation, you're getting a new thing. Okay, so on rotation, I'm getting a new thing means what? The first bead goes to the, let's say, 1 plus eighth bead, right? Okay, 1 plus xth bead if I rotate by x, right? So if it does not change in the rotation, 1 and 1 plus x must have the same color. 1 plus 2x must also have the same color. 1 plus 3x must also have the same color. And so on until 1 plus p minus 1x must also have the same color. But like, since it's rotation by x and it's mod p, you're covering everything. You're saying that everything should be the same color if it does not change under rotation by x amount. Does that make any sense? Let's try a
Yeah.
case.
Yeah,
You have,
sure.
let's say
Yes.
you have 5 beads. Okay. How much is 5? Yeah, this much. So you have 5 beads. Let's say 1, 2, 3, 4, 5. And now I rotate it and say that it stays the same. Let's say rotate it by 2. So 1 goes to 3. That means like 1 and 3 must have had the same color. But 3 goes to 5. So 3 and 5 must have had the same color. But 5 goes to 2. So 2 and 5 must have had the same color. And 2 goes to 4. So 2 and 4 must have had the same color. So basically everything had the same color. If like
Yeah.
rotation changes nothing.
Yes.
So if rotation changes nothing, then everything has the same color. And if rotation is changing something, then you make groups of p, right? Just because you could have rotated by nothing or 1 or 2 or 3 or p minus 1. So there are a things which are in groups of just themselves, in which rotation changes nothing. And there are a to the p minus a things which are in groups of p, in which rotation changes things. So that's just the p. Make sense?
Yeah.
Awesome. So this is the necklace proof. Okay, I'll skip another proof for the sake of it, just for time reasons. So there is one proof of by considering the function fa x, which is given by the fractional part of ax. Okay, for x in 0, 1. Okay, and for this you can check that there are a points that take the same value, like fa of x is equal to x for a things. And you can check that for f a to the p x is equal to a to the p x. There are a to the p fixed points. So the fixed points of this under, like if you do fa on them instead of fa to the p, you get cycles of length p instead for a to the p minus a things, and cycles of length 1 for a things. So again, in the same way, you'll get a to the p minus a divided by p. I know it was very fast, and it's probably not a good way to explain, but this is one of the ideas, and you can check it out on, I don't know, just I think you'll find it on Wikipedia, even if you look for it. Okay. Fixed point is f of x equal x. Then x is a fixed point of f. Like under this function, it's a fixed point that it goes to itself. Okay. Fixed. This is another idea that you should really know. It's not, I'll just put this in for those who are interested. This is called Lagrange's theorem. Don't worry about it. And yeah, so what we'll consider is, consider 1, a square, a cube, and so on, up till, let's say, a to the k. Okay. And now, assume that a to the k plus 1 is congruent to 1, mod b. Do you see why such a k would exist?
Well, within
Could you repeat?
we can easily prove by pigeonhole.
Yeah, perfect. You can argue by pigeonhole. You can just consider this infinite set, a square, and all the powers. And if the one does not, like, okay, since there are just p minus 1 possibilities of remainders, right? Since there are only p minus 1 possibilities of remainders, at some point it must repeat. And let's say it repeats at some point. Let's say a to the I is equal to a to the j. Then you'll get that a to the j minus I is congruent to 1 mod b. Okay. So you'll get at some point this happens. Okay. So we consider the smallest such point where it happens and just consider this set of things. Okay. Now let's see something else. This is a set of things. Okay. Let's call it k minus 1 actually, so that a to the k is congruent to 1. How many things are there in this set?
K minus 1.
K things. This is a to the
Yes,
0,
K.
right? K things. So if I can show that k divides p minus 1, then what will I get? That since a to the k to the p minus 1 upon k is congruent to 1 to the p minus 1 upon k is congruent to 1 mod p. So I'll be done, right?
Yes.
Yeah.
So I just need to show that k divides p minus 1. So what I do is try to make sets which are roughly of this form, that 1 a square. But I can't do that exactly. So what I do is I consider sets which are just one small thing multiplied in the beginning, b ba square, and so on up till ba to the k minus 1. Yeah.
Is B
Is-
relatively prime?
B is just some element from 1 to p minus 1 for now.
So it's relatively prime.
Yes, yes.
Sorry.
So we just consider sets of this form mod p. Okay. Now this, let's call this set, I don't know, xb. This set is x1. Okay. So now I claim either xi equal xj or xi intersection xj is nothing. For any I and j, either xi is xj or they are completely different. Just a revision, x1 is just 1 a square a cube all the way up till 8 to the k minus 1, where a to the k is equal to 1 mod p. xb is just n all the elements multiplied by b of this set.
Excuse me.
So
what's
how
the
do we prove this?
What's the Lagrange theorem?
This is, I'm saying this is basically the proof of Lagrange's theorem, in case you know what it is. If you don't know what it is, does not matter.
Can I tell you how to prove it?
Because like earlier we also used this property that if you have the set 1, 2, 3 up to p minus 1 modulo p, then if you multiply it by a number a, then the new set that you get will be a
You
permutation
also
of
reduce
the
modulo p the same.
earlier one.
Yeah.
Yeah. So in some sense, yes. So observe that if they're, we only need to show that if they share even one common element, then the entire set is the same, right? I don't need to show anything else. So if they share one element, what does that mean? I into a to the k1 is congruent to j into a to the k2. Yes? Mod b. This is the common element they have. So what does this mean? I into a to the k1 minus k2 is congruent to j. So j is in xi. But then j into a to the r is in xi. So all elements implies xj is a subset of xi. Does it make sense?
Yes.
Yes.
So, but they have the same size. Both are k-sized things. So, yeah. So you have divide. So what you have been able to do is find sets of size k, which are either disjoint or are completely the same. So we put all which are completely the same in the same group and just ignore. So we have a few groups of size k. How many groups of size k do we have?
4, 5.
Okay, not like I'm not like for a general p.
Yeah.
P
Okay.
minus 1.
Yes, but like see that every element is in exactly one group now, right? Because we have just merged everything which was the same. But everything is in exactly one group. So there are p minus 1 upon k groups. Just because everything has k elements and there are p minus 1 things and everything is in exactly one thing. Does that make any sense?
Yes.
Yeah, so you get that p minus, so this implies k divides p minus 1, which is what we desired. So we are done. So we have a to the k is congruent to 1 implies a to the p minus 1 is congruent to 1. Not p. So we're done. This is also what's called Lagrange's theorem, and this comes in useful in group theory, whatever that means. Just a thing to know. Okay. All right. So I'll go over Wilson's theorem now. So what Wilson's theorem tells you is that p minus 1 factorial is congruent plus 1 is divisible by p. Sorry for rushing there at the end. I think we have to finish a little faster. I'll just try to do Wilson's, and I don't know if how many of the Cauchy's proofs will AMGM proofs will do. But let's see. So p divides p minus 1 factorial plus 1 is what we want to show. Okay. Now, one thing that we saw just previously here, that if we just consider just powers of p, we are eventually getting back to 1, right? So there is some element that if I multiply a by that, like a to the k minus 1 into a is congruent to 1, mod p, right? And similarly, here also we saw that since you have 1 to p minus 1 and you're multiplying everything with a, you're getting back the same set. So there exists a b such that ab is congruent to 1. Yeah. So So the point is, for every x exists a y such that xy is congruent to 1 mod p. So this is a nice thing to have just because now you can pair these things up. You can consider x comma y pairs such that xy is congruent to 1 mod p. Right? How many pairs are there of this form?
With total,
Infinite.
not
Mm,
infinite. It will be like
No. We are only considering the set 1 to p minus 1.
keep so
P minus 2.
Y p minus 2 pairs.
P minus 3 divided by 2.
Y p minus 3.
Should be p minus 1 because every element will have exactly one inverse.
Yes. So that is one thing to be careful of. Here you're assuming that x and y are not the same thing. Right? But it's very much possible that x and y are the same thing. So if x and y are the same thing, then you have x square is congruent to 1 mod p. That means x is 1 or minus 1. So you have to consider the numbers which are not 1 or minus 1. So you have to only consider the set that is 2 to p minus 2. Okay. So these are p minus 3 things and they split into pairs of 2. But observe that each pair multiplies to 1. Right?
so it's
So
like
if
like if you multiply each x with its inverse from the same set, we'll give you one pair of ones, right?
yes.
So what will happen is you take the product of all of these, mod p will remain the product will get p minus 1 factorial, and the last two, if you multiply them together, you'll get a minus 1. So you get this like p minus 1 factorial is congruent to minus 1 mod p, which is exactly
Yes.
what the theorem states.
Exactly. So you get that you have these p minus 3 by 2 pairs which all multiply to 1. Then
Yeah.
1 obviously multiplies to 1. So the only factor that is not 1 is this minus 1. So you get that p minus 1 factor here
And by J-
is
by
congruent to
Lagrange
minus 1.
process.
Yes. Does it make sense?
Yes.
All right. So this is one very nice proof. And then you can also do via polynomials. So what is the theorem saying? Okay, one thing is like, okay, observe that this thing, minus 2, x minus t minus 1. This is always divisible by p, right? If x
Yeah,
is like
because
not divisible by p,
this is p consecutive numbers, right? So one would be okay, sure. So we'll have
okay,
like
so
one factor. K is p consecutive numbers. So one of them has to be a multiple of p.
exactly. So since these are p consecutive numbers, at least one of them is a multiple of p. Okay. And now consider x to the p minus x. This is also always a multiple of p
Right.
by Fermat's little theorem.
Yeah, right. It is.
Okay,
Yes,
so what is the degree of this polynomial that I have?
degree should be p, right?
P minus 1 because the terms that the power of p will cancel.
It's p. Should be
Is it
p.
degree p?
The degree of the polynomial should be p. Yeah, it is degree P. There's like P.
P minus 1.
Oh, sorry. Yeah, should be P minus 1. The minus x, like x, talking x about. Net is.
Exactly. So this is
I'm definitely. That's right.
I'm not sure what happened. Give me a sec. Okay. Okay, Rohan, everything okay?
note down an incredible amount in a second. I have no understanding of why.
What? Rohan, is everything okay?
Yeah, it's just like computer's behaving very slowly right now. I have no idea why.
Uh, yeah, I've been there.
Like, yeah, it's not responding to things as well. What can you see? Can you see the whiteboard right now?
No.
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 Um, okay, give me 5 minutes. I'll rejoin. Yeah, I think I'll do that. Thanks. Hi, am I audible?
Yes.
Awesome.
Yes.
Yeah, let me know if when you can start seeing my screen again. Just a sec. Can you see my screen now?
No.
Yes.
Now, yes, yeah.
Awesome. Okay. So observe that this is some polynomial of a degree p minus 1. Degree where degree f is p minus 1. But p divides f of 0, f of 1, f of 2, all the way up to f of p minus 1. Right? Like it divides it for all numbers, so it divides each of these. Yes?
Yes.
Yes.
So the thing is,
Yes.
in mod p, if you have like these p things, like all remainder on all remainders are being divisible by p, then the number is always divisible by p, in the sense like each of the coefficients are also divisible by p. Okay? If it's a degree p minus 1, like it's less than, like you can, like you say, right? Like you have, if you have n roots, then the degree of the polynomial is at least n, right? Same you can argue in mod p. You have p roots, but the degree of the polynomial is less than p minus 1, like less than p. So it must be 0 mod p in the sense of the polynomial itself. So what you'll end up getting is, if you look at the coefficient of x, that x into p minus 1 factorial plus x is, so what is the coefficient, is equal to x into p minus 1 factorial plus 1. This is divisible by p. So you get Wilson's theorem. Okay. Does that make any sense? Awesome, awesome. Right. Okay, wonderful. You can try proving this result. It's not hard to prove that the degree argument I just said. Okay, not hard in the sense of like uh, considering the content we are doing today. Otherwise, obviously, it's not a natural argument. Right. So combinatorial proof. So now we want the p minus 1 factorial that all of you were claiming to come up naturally instead of a to the p, with the same type of thing that we have p things around a circle and rotations are okay. So call this thing 1, then 2, all the way up to. So what we look at now is the number of paths that start from 1, go to everything in some weird manner possibly, and return to 1. How many such paths are there? That go to everything and just return to 1. And go to everything exactly once.
P minus 1 factorial.
Exactly. P minus 1
Divided
factorial.
by 2. P minus 1 factorial divided by 2.
We can double count, it's fine. Like I can make this directed edges. Like all these edges could be directed for me. Okay. Is that fine?
Yeah.
Okay. So these P minus 1 factorial paths. And again, I want to say that the paths will, like I want to put the paths in the same set if they are rotations of one another. Right? So how many paths are there of this form which do not change under rotation? No. How did you get that? What does that mean? We want to consider firstly the paths which do not change under rotation, and then we'll consider the paths like we'll group everything in groups of P which change under rotation. Okay, so let's see what happens if I change 1 to 1 plus x, right? What do I get? Initially, let's say 1 had an edge going to 1 plus y. Okay, now that means 1 plus x has an edge going to 1 plus x plus y. Yes.
Yeah.
Okay, but 1 plus x went to what? 1 plus 2x, right? So there must have been an edge from 1 plus 2x to 1 plus 2x plus y, right? But this went to 1 plus 3x. So this must have had an edge from 1 plus 3x to 1 plus 3x plus y. But this went to 1 plus 4x, which must have had an edge to 1 plus 4x plus y. So this is basically saying that all edges that you have initially are of the same length, right? Because I can continue this argument all the way up to 1 plus p minus 1x, which takes an edge to 1 plus p minus 1. Why is 1 going to 1 plus 2x? Because I'm rotating by x, right? X is the amount of rotation I'm doing. So under rotation, 1 plus x is going to 1 plus 2x. Under rotation, 1 plus 2x is going to 1 plus 3x.
Then what do you mean by 1 is going to 1 plus y and 1 plus x is going to 1 plus x plus y?
Oh, this is like the edge. Sorry, I should use a different color perhaps. This is the edge in the graph. This is the edge in the graph. These are the edges in the graph. And those are the things under rotation.
Okay.
See, I said that it does not change under rotation. So if 1 had an edge to 1 plus y, I went from 1 plus x, 1 went to 1 plus x, right? And 1 plus y went to 1 plus x plus y. So that must still be an edge. And if that is still an edge, it was also there in the previous graph that I had. So 1 plus x to 1 plus x plus y was an edge. So I've gotten all edges this way by saying that all edges are of equal length, right? Okay. So since all edges are of equal length, there are just p minus 1 possibilities for this length. So we get that there are p minus 1 factorial minus p minus 1 upon p plus p minus 1 possible paths we have, which are not changing under rotation. Okay, like if you also consider the rotation of this, you get everything. So again, that you get that p divides this quantity. So p divides p minus 1 factorial minus p minus 1 implies p divides p minus 1 factorial plus 1. Does that make any sense?
Yes. Complete sense.
Yes.
All right, sure. Yeah, so this is Wilson's theorem. I'll probably not be able to go over all the proofs of AMGN. So I'll just go over one and then I'll leave you to it. And
44 back on induction.
I think that's one you should look up on your own. So I'll just mention them. So you have one direct induction, which takes n to n plus 1. Okay, there are two ways of going from n to n plus 1 directly. Then there is backward induction, which is Cauchy one. Which says that you can go from 1 to go to 4, and you can go to 8, and you can go all the way up till whatever power of 2, and so on. And you can go from n to n minus 1. So like if it's true for 1, it's also true for 2. If it's true for 2, it's also true for 4 and for 8 and so on for all powers of 2, which is the number of variables. And if it's true for n variables, then it's also true for n minus 1 variables. So the point is, if you can, like when you try to prove AMGM for just 3 variables, if you don't know the factorization, then it's already a very hard job to go about it. But one thing that while proving AMGM, you can neatly observe that, okay, if I can do it for 2, then I can definitely do it for 4. Because it's the same argument repeating. Which is just saying that, okay, x1 plus x2 by 2 plus x3 plus x4 by 2 upon 2 is greater than equal to root x1 x2 plus root x3 x4 by 2, which is greater than equal to root of x1 x2 x3 x4 fourth root. Yeah, this is something you get immediately almost, right? So you can, if you can do it for 2, you can do it for 4, and I can repeat it for 4 to go to 8 and then to 16 and so on. And you can also check that if you can prove it for n variables, it must have been true for n minus 1 variables as well, because you can just set one of the variables to be GM of the other n minus 1 variables, or you can set one of the variables to the AM of the other n minus 1 variables. So this is Cauchy backward induction. So this is one proof that I find really cool and which is very surprising to me. This Paulius proof.
George Borda.
I'm not sure what's the first name.
The one who wrote the book How to Solve It.
I am not sure. I wouldn't know. Okay, anyway, the point is, in general, we have this inequality. E to the x is greater than or equal to x plus 1. Okay, it's not a very deep inequality. It's just like if you have this exponential function, which is e to the x, if you, and then it has a tangent here, which is of slope 1. It's not a very deep inequality by any means, but it's a decent result. So e to the x. Asmita, you are unmuted. No problem. E to the x is greater than or equal to x plus 1. This is an inequality that we have. Okay. Now consider the variables a1. Okay, so sorry, I was working with x1, x2. So your variables are x1, x2, xn. Let's say g is equal to the gm of x1, x2, xn. And a is equal to the am of x1, x2, xn. Okay. This is fine. Just like defining stuff right now. Okay. So observe e to the x1 by a minus 1 is greater than or equal to x1 by a. Yes?
Yes.
Okay. E to the x2 by a minus 1 is greater than or equal to x2 by a. And I can write these for everything, and I'll get e to the xn by a minus 1 greater than or equal to xn by a. Yes. So I just multiply both sides. And I get e to the x1 by a minus 1. Asmita, I can't hear you, and yeah, there's too much disturbance. Okay. And let's dot xn by a minus 1 is greater than equal to x1, x2, xn by a to the n. Yes? ये L क्या है? Where is L? That's 1. I don't know.
No, that's E. Your E just like L.
Oh my god. Okay. Okay. E. Sorry. Yeah. So you have this inequality. Yes. Okay. What is this? This is e to the x1 plus x2 plus xn upon a minus n. Just think of it as some number which has this inequality. Don't think too much about this. There's just some number e which has this inequality. Greater than or equal to, what is this? G to the n upon a to the n. To observe that this is also n by definition of a. x1 plus x2 plus xn is just n into a. So 1 is greater than or equal to g to the n upon a to the n implies a greater than or equal to g. So you're done. Yeah. Okay. So one last idea I'll show. So yeah, I know. So this is just an idea I want to tell. I'll not be discussing this because I want to end by 3:20. Okay. So observe that, okay, if I fix the sum x1 plus x2, not natural, just it's not a natural number. And yeah, you can't really directly define it that way because you can't show existence that way. But such a number does exist. Yeah, E is rational. E is even transcendental. E is a scary thing. So e to the x is greater than or equal to x plus 1. So I'm just plugging in x equal this thing. Yeah, something like that. So x1 by a, x2 by xn by a, and I just multiply it and I get the required inequality. Okay, so now the other idea is this. Observe that, okay, if x1 and x2 and xn are variables, okay, and I fix their sum. Let's say I fix their sum is equal to na, which is some constant, okay. Now what I'm just trying to do is increase g, okay. I'm just trying to say, I'm trying to find the maximum g possible, where g is the gm. And you want to claim that the maximum g possible is a, right? That is the claim that you have. Agree?
So maybe we can prove it easily just by considering some factors are greater, like a plus k, a minus k in this form.
What?
Like we need to prove that GM holds when all the terms are equal to each other. So
yeah,
we can make the generalize this claim to that x and x2 and these are all equal. If they are not equal, we can consider a standard deviation from average of them Like
Standard deviation. What does that mean here?
deviation from AM. Like some number will be AM minus K, some will be AM plus K, some will
Okay,
be AM
sure.
minus
Not
K1.
you. They don't need to be the same thing.
No, they
Changing the
don't need to
symbol.
be the pairs, but then we can easily prove algebraically.
Sure. Yeah, that's something like that you can do, but in that you are inherently assuming this inequality in some sense. You have to prove that makes sense.
No, I'm not I'm just
Like,
replacing xn and all the x1s and xn by their deviation from the average.
sure. And then what do you do?
Then I go on to prove this that the dot product will be
How?
shorter than or equal to the average.
How?
Maybe like for some squares, we used to prove that some a b is equal to 24 and they are of the form a k minus and k plus a. So for the maximum of it, then both need to be equal.
You're on the somewhat right track, but this way you can't directly argue anything.
Okay.
Yeah, like inherently you're basically just rephrasing the problem than actually making progress on it. Like the idea is there somewhat, but not quite. Okay. So let's say someplace it's maximized. What I'm not going to prove is that it's maximized someplace. That's one thing I'm just pretending happens, that it's maximized someplace. But if it's maximized someplace, we claim that they all must be equal. Okay. So let's find a place where it's maximized. Let's say x1 plus x2, like x1, x2, xn are some things such that this thing is maximized. Such that x1, x2, xn is maximized. Then what do I do? Then there are some xi and xj such that xi not equal to xj. Otherwise, all are equal, and right? Then I basically have AMGN if all are equal.
Yes.
So I'm just assuming that there are some xi and xj which are not equal. So what I just do is replace both of these with xi plus xj by 2 and xi plus xj by 2. Observe that the sum remains the same and the product by 2 variable AMGM has increased. So the product couldn't have been maximized if any two are unequal. So if the product is ever maximized, it must be when all are equal. Does that make sense?
Yes.
Yeah. So one thing I did not do is that show that it's maximized at some place. But if you can show that it's maximized at some place, then this is the point where it's maximized. Okay.
So it involved averages in some way.
What?
Like it involved averages in some way.
Yeah. That's why I said you're on the right track, but the way you were doing it, it won't directly extend because then you're just rephrasing the problem in some sense.
Hey, can we prove this inequality by taking log both sides?
Yes. So there is a way of doing that.
Yeah,
That's another proof of it, which is, I think you're saying that log x1 plus x.
yeah, by taking convexness of log, it
Yeah.
converts.
Yeah, I know what you're saying anyway. So you want to claim this upon like log and this is greater than equal to what? Can you tell me
It
about
will be
One
it?
by
more like
n,
log
one
x1
by
plus log
n
x2.
log of 1 by n
1 by n.
log of x1 plus
Oh, but maybe 1 by n will not be here.
Is this what you're saying?
no, when we take log of geometric series wala, so exponent came down.
Yeah,
Power,
1 by n
power.
came down, right? It was x1, x2, xn to the 1 by n.
But you need to take n on the other side. Yes, convections.
Yes, this is the thing you're saying. This is what you're claiming, right?
We can cut also n.
We can
How do
we
you cut?
use equal
How
value
do you cut?
principle?
What n do you cut? Sorry, what is it?
No, uh, when we take n to
Hello,
the
can
other
we
side,
take
we get.
equal value principle here?
Can you be cut?
What is equal value principle? Just calm down. Once,
Okay.
one of you speak.
Okay.
Aditya,
Okay,
go on.
okay. Okay, you just continue.
All right. Anurag, what were you saying?
We need to involve n minus 1 equal value principle somehow here.
No,
Using
no, no, no,
convection.
no, nothing like that.
Okay.
So this is Jensen's, in fact. So what does the function of log look like? Like, what does
It's
log
like the derivatives decreasing.
don't just let's be a little hand wavy right now because not everyone is familiar with what you're trying to say.
It's like the growth, the rate of growth is decreasing.
Right. So the graph of log looks like something like this, right? And yeah, it grows slowly as your number becomes large. So what they're saying is, if your function is like log x1 is some point here, log x2 is some point here, log x3 is some point here, and so on, right? If you have this type of shape, and then you consider this polygon and you consider it centroid, right? This centroid lies somewhere here, which is 1 by n of log x1 plus x2 plus xn. But this is below this graph. So the log x1 of the average is above it. That's all they're saying. So what they're saying is like the convexity thing they're saying, oh, just the average of all the points. If you consider any coordinate system, just take the average of all the points. Yeah. So what they're saying is that if you consider any few points on this and consider the polygon created by that, that polygon is convex. That's all they mean by
Yeah,
convexity.
but on the left hand side, we can assume that we have a wait, we have a log of all mean of xi's, and then the right hand
That
side
that
we
is
have
what
a
this is.
non. Okay, we have a mean of all log xi's. So by
Which
language of expectation, they are smaller. This side, right
no
side
no
is smaller.
no. What does that mean? That's not. What does that mean? Language of expectation. Sorry, what?
No, by generally that if x is a number, then log x is always smaller than.
What do you mean by that? The x is a number, log x is always smaller. This is a very different structure. Like here, you don't
Oh,
like you're comparing within the log.
okay.
You're not comparing x and log x. I don't know what you mean. Are you saying this expectation of uh, log x is less than equal to log of expectation of x?
Yeah. No,
Uh,
no.
is this what
On.
you were claiming?
Yeah. Yes.
Yeah.
Yes.
See, this is basically the result you're trying to prove. So you can't directly use that. I mean, this is basically like you're rephrasing the result, which is not exactly the thing to do. That's not a proof. Rephrasing the result is not a proof. All right, so this is what I wanted to talk about. I'll stop sharing now. I had to finish early today. Sorry for that. And anyway, we didn't have too many people today.
I'll end
Oh.
recording, right?
Yeah.